Therefore, we propose combining a smart light with Arduinos that has a motion sensor to detect whether the user is washing hands and change the color of the light bulb when the user has adequately washed hands for more than 20 seconds.
Our design consists of 5 main components and is centralized around the Bluetooth Low Energy technology. In order to control the light, we require an accelerometer, which is the MPU 6050, a Bluetooth module in master mode, which is the HM10, a microcontroller for processing, which is the Arduino Uno, and an external 9-volt battery. The microcontroller manages the accelerometer data as well as the commands that the HM10 sends to the light bulb. For hardware limitation reasons that will be expanded later, our ideal setup would involve the same components as before, except instead of a regular Arduino Uno, an Arduino Uno Wi-Fi Rev 2 model with built-in Bluetooth would be used, removing the need for the HM10. Here is a state system diagram that shows what our Arduino microcontroller software is doing. It starts in standby mode, and when the user comes into proximity of the sink, it is switched to proximity mode. If the user then leaves again, perhaps they just came to brush their hair, it'll go back to standby mode. Otherwise, if the user starts washing their hands, it'll go into washing mode where a 20-second timer is set. At this time, the Arduino sends a command to the Bluetooth module to change the color of the light to indicate that the timer's running. If the user stops washing their hands partway through but stays near the sink, the timer will pause and wait for the user to resume. Finally, the user knows that it's safe to stop washing their hands when the light turns back to its normal color, where it goes into cooldown mode and waits for the user to leave the vicinity again, since they may stay around to do other things before leaving. Each Bluetooth device has a Bluetooth address, and the peripheral in particular has services with different characteristics that control different attributes of the device, such as the color of the Bluetooth light bulb. In order for us to control the light via the Arduino, we need to first figure out what this information is. To find our desired information, we use Max Packet Logger that allows you to watch the Bluetooth traffic going in and out from your iOS device. Here you can see packets of data being sent back and forth to and from Bluetooth peripherals. By turning the light different colors using the phone, we can figure out what traffic is from the light and deduce our desired information from it. At the top, you can see the Bluetooth device address ID, which is required for the initial connection to the light. Further down the page, you can see a packet of information that the phone wrote to the light in order to change characteristic 002B, which is for the color of the light. You can even see what value it was set to, which is exactly what we need to send the information ourselves. Using all of this, we are able to communicate with and control the light bulb.
We classified the hand-washing gesture by using a machine learning-based approach, which combined PCA and SVM. PCA is principal component analysis, which reduces the dimensionality of a dataset while retaining the variation present in the dataset. Additionally, we used SVM, which is support vector machines, which finds a decision boundary that maximizes the margin separating the positive from the negative training data points. In this case, positive training points is the hand-washing gesture, and the negative training points are non-hand-washing gestures. The training data that we used was we recorded many events that were hand-washing gesture events and labeled them as hand-washing. And then we recorded other sync-related activities like brushing our teeth or brushing our hair, washing our face, or even just standing still in front of the sink, and labeled them as other sync-related activities that are specifically not hand-washing. And we use this training data to classify what is the hand-washing gesture. We used a 6-axis IMU sensor, the MPU 6050, which has a 3-axis accelerometer and 3-axis gyroscope. During training, we recorded feature vectors for each gesture, hand-washing and not hand-washing, and used those to train the classifier. And during testing, we recorded feature vectors for each gesture and predicted which classes the gesture is in.
This is how the fully functioning SmartLight would work. The user is in range. The device is now in proximity mode. User begins washing hands. The device switches to washing mode. The light turns red, and a 20-second timer is set. After 20 seconds, the light turns blue and switches to cool down mode. The user is no longer in range, in standby mode.
For our evaluation metrics for gesture classification, we use precision and recall. For precision, we got 14 out of 19, which is equal to 73.68%. This means our classifier correctly classified 14 events as hand washing. 19 is the total number of events that our classifier thought was hand washing. For recall, we got 14 out of 15, which equals 93.33%. 14, again, is the number of events that our classifier successfully classified as hand washing. 15 is the total number of events that were actually hand washing.
Parts break and Arduinos break. A few days before the end of our project, the only module of Arduino that we have that could work with the code that we were writing completely broke. And because of that, we are not able to film the demo that we wish we were able to show you. Second of all, reverse engineering can be really hard. Companies want to make sure that what they're doing is unique and that other people cannot figure out what they're doing. Therefore, when my partners are doing the sniffing part of trying to tell how the Bluetooth packets are being sent to the SmartLight, that took a lot of time. Third of all, if you are going to run something that is very memory heavy, like a machine learning classifier, you will be limited by the memory of the device you use, in our case, the Arduino. We actually had to decrease the kernel for the classifier so that it would fit on the board. And that probably reduced the accuracy of the algorithm.